Today we shall conduct one more experiment, and the name of the experiment is linear variable differential transformer. In short, it is called as Lvdt. So the aim of the experiment is to calibrate the given linear variable differential transformer. The apparatus that we are using in this experiment is Lvdt, micrometer and the slip gauges. So this experiment is conducted in two parts. First one by using the micrometer and second one by using the slip gauges. Now let me explain first what the Lvdt is. So it's a linear variable differential transformer. So there will be a non-contacting core will be there, and this moves inside a hollow cylinder. So where the primary coil is connected at the center and two secondaries are on either side of the primary coil. So now this ferromagnetic material, when it moves to the left and right, so this is the right extremity and this is the left extremity. So when the core moves to the left, though the flux cut by the secondary coil S1 will be more than the flux cut by the secondary coil S2, and the difference of output is shown in the meter. So when the core moves to the right, so the flux cut by the secondary coil S2 will be more than the flux cut by the secondary coil S1, and the difference will be shown in the output. So when the core is in the middle position, it is called as the null position. So then the flux cut by the secondary one and the flux cut by the secondary two through the core is going to be same, but which will be out of phase, that is 180 degrees out of phase. Therefore no difference will be shown or no output will be shown in the meter. So this is how the Lvdt is going to function. So this is the Lvdt. Now I will explain first half of the, you note down the first half of the tabular column. So this is with respect to the micrometer, that is as I told you earlier, the experiment can be conducted in two parts. First one by using the micrometer. Now this is the micrometer. So now this is the thimble. So when we advance this, this is the angle. So when we move this one, so this moves, when we move this one in the clockwise direction, this advances. When we move in the anti-clockwise direction, this comes back. So now what is the least count of this one is, so this is the main scale reading. So when we rotate this by one complete this thing, that is divided into 50 divisions. So this is the thimble. So when we rotate this by one complete revolution, so that entire this thing is divided into 50 equal parts. So one division on the thimble is equal to 1 divided by 50, or this will be 2 divided by 100. So that is equal to 0.02 millimeter is the least count of the micrometer that we are using. So now what we are going to do is, we are going to give the input as say 0.5, 1 millimeter or 1.5 millimeter, 2 millimeters, like this. So when we advance this one, this is the rod that is connected to the core here. So this starts moving. So that is, this is going to push this plunger, and this is going to move in this direction. So then the flux cut by this through this core with that of the secondary S2 and secondary S1. So this is the primary coil. So the difference of EMF will be indicated by this scanner. So now that difference of reading will be recorded here. So this is called as the Lvdt reading, and this is the micrometer reading. So that means we are increasing the values by 0.5, 1, 1.5, 2 millimeters, like that, and accordingly the core will start moving in the left direction. First of all, the core will be adjusted to what you call null position while conducting the experiment, and after that it can be done like this. So this can be done in increasing manner and also in the decreasing manner, in the sense that, so now we have gone up to, let us say, 10 millimeter. So from 10 millimeter in the decreasing mode we come back. That is 10, 9.5, 9, 8 up to 0. So it can be done in two ways. It can be done in two ways. So now then we are going to plot the graph of what you call the micrometer reading. Micrometer reading will be here, and this is the Lvdt reading. So a graph of Lvdt reading versus the micrometer reading. And then we are going to find out what is the difference, whether it is actual Lvdt reading matches with the micrometer reading or what can be indicated by this graph. Then we are going to find out the percentage error versus the micrometer reading. So supposing, say, if we have got what you call some value 23.4, then for this one, what is the percentage error that is included in the value can be found out from this graph. Once when we know for different what you call readings of micrometer here, what is the percentage error to be included. So in the sense that, for example, for 23 millimeter, so this is the actual value 23, then for this, what is the percentage of error should be included. So that should be multiplied by 0.03 or 0.04, something like that. So then you are going to get, this is 0.04, then you are going to get 23.4 millimeter like that. This is one part, that is using the micrometer. You can do it in the increasing order and as well as in the decreasing order. Very similarly, so here we make this 0 of the distinct to coincide with the 0 of the main scale, and now we are inserting the slip gauges. Slip gauges may be, again, as I told you, it could be 1 mm and then 1.5 mm, 2 mm like that, and that will be inserted here. That will be, this is the slip gauge. Slip gauge will be inserted here, and no more disturbance of this thimble now. So now we insert this here because this is movable. This is movable. By moving this one, so we are going to insert this. Now depending on the thickness, let us say this is 1 millimeter. Now the core would have moved by some distance in the leftward direction. Then what is the difference between the EMF between S1 and S2 will be recorded in the scanner, and that will be recorded here. Again, same way. So here we are giving the rotation in the form of 0.1, 0.2, 0.3, 0.4, 0.5 like that, or 0.5, 1, 1.52 millimeter like that. And here we will be having the standard slip gauges, and we are inserting those standard slip gauges here in between the movable anvil and the fixed anvil, and we are getting the readings here of the Lvdt. And similarly, so we are going to draw the graph of slip gauge reading. So here comes what you call the slip gauge reading. Slip gauge reading, this is Lvdt reading. So we are trying to find out the calibration graph of for this Lvdt. This is the Lvdt reading, and this is the slip gauge reading. Then percentage error again is the slip gauge reading. So this is how the experiment is conducted. Again, in this also we can do it in the increasing mode and also in the decreasing mode, in the sense that now we have started with 0, 1, 1.5 to let us say up to 10 mm, and then this is the first part. In the second part it starts with 10 mm and slowly reduces to 0 or 1 mm. Slowly we come back to 1 mm. So this is the increasing mode and this is the decreasing mode. Very similarly, here also, if it is 10, then we come back to 1 millimeter. So this is how this thing is conducted in two methods. One by using the micrometer, and another one by using the slip gauge. We are trying to calibrate the Lvdt, and then we plot the graph of these two graphs, and we find out what is the characteristics of the Lvdt. Thank you very much.
Hello everyone. Now we are going to conduct an experiment, Lvdt linear variable differential transformer. Here we have a setup, we have a primary and secondary coil, and we have a core movable distance sensor here. We have a digital indicator here. We have a one adjustable setup, and we have switching over knob here. So how to conduct this experiment? First we should know how to read the micrometer. We already explained in the calibration of micrometer also. Even though I will tell you once again, first we have to find least count of the micrometer. How to find the least count of the micrometer? 1 MSD divided by total number of PSD. What is 1 MSD? 1 MSD is 0.5 mm here. 0.5 mm is divided here by the 50 divisions. So the least count of your pitch scale division is 0.01. So initially what I will do, I will keep it my micrometer in the reading of 10. It means I want to place my core as a middle, and I will take towards to the forward and towards to the backward to know the characteristics of a Lvdt while moving towards to the secondary coil or primary coil, whatever it may be. So to find that, what I will do, I will find a null position here. How to make a null position? You can place a 10 here, and using a knob, you can see here there is a knob is given. By giving a more volts or more power to the system, you can make it that as null position. Now we have a tabular column. The actual reading is we have two type of tabular column. One is for micrometer and another one for slip gauge. Now I will conduct an experiment for a micrometer. What I will do, I will just rotate my micrometer to the 0.5 mm towards to the backwards. So what I will do, I am rotating one rotation from 0 to again 0. I will come back here. So if I move 0.5, so it's giving some reading here. Don't worry about sign, plus and minus, you can plot it in a graph. So make a center line towards to the backward, plot it in the right side, towards to the forward, write it in the left side. Okay, so it's showing how much here. While moving 0.5 mm on here, it's mentioning 0.51. Like I will now I will move 1 mm. Now what is the reading? 1.02 it is showing. Next, the actual reading is 1 mm. The measured reading is 1.02. You have to write it down in a tabular column, all these readings. Next, I will move 1.5 mm. Now I moved 1.5 mm. It's showing 1.53. Next, I will move 2 mm. It's showing 2.03. Next, I will move 2.5, 2.54. It's reading 2.54. Next, I am reading my actual value is 3.0 here. It's showing 3.04 here. The measured value is like this. So I will come back to the null position again. This is my null position. Again I am moving towards to the front. So 0.5 mm I am moving towards to the forward. So it's showing 0.5 only it's showing. Now I will move 1 mm. 1.01. I moved 1.5 now. 1.52. I moved 2 mm. 2.02 it's showing. .5 mm I moved. 2.52. Three mm I moved. 3.03. Okay. Again I will come back to the null position. I hope you noted down all the readings. So I came back to the null position. This is how to conduct an experiment of Lvdt, calibration of Lvdt using micrometer. Okay, theory part has been already explained. Only you need to take the readout. Now you have to plot a graph. What is the actual reading here and what is the measured reading here? You have to plot a graph on this. Similarly, we can use a slip gauge. Instead of moving a screw caliper, you can use a slip gauge to measure what is the actual value of this. Example, I am taking it to 1.24. This is 1.24. I have 1.24. I am placing the 1.24 in between this. Now what must be my reading? It should be of 1.24. But it is showing how much? 1.25. Okay. So 1.24 is the actual reading. Measured is 1.25. Like that. I am taking 1.29 or I will take 1.31 I will take. 1.31 I will take. I am just placing a 1.31. 39. It's showing 1.33 here. Next, in the 0 position, careful while you are handling this. I will take 1.41. It's showing 1.43. I took 1.41. It's showing 1.43. Next, I will take 1.49. I will take 1.49. It's showing 1.52. Next, I will take 2.5. It's showing 2.53. Okay, so now I told you the actual reading using a slip gauge and what is the measured value of the system. Okay, plot a graph, actual value versus measured value. Okay, so find the error and percentage of error, also plot the graph. Thank you.